Hi everyone, welcome back. In today's video, we will start designing circuits in Cadence. So we'll start by setting up the Cadence environment and we'll discuss how chip design is done on Cadence and the very basics to getting started. So let's, without any further delay, let's get started right away. So I'll start by talking about something called a PDK, which is a common term used in chip design. It's called a process development kit. And the process development kit is a comprehensive set of files and resources provided by a semiconductor foundry that contains all the necessary information for designing integrated circuits using a specific fabrication process technology. So let's say you decide, okay, you want to do chip design, you don't know anything about chip design. So you know some basics about circuits, and you want to do what is called a tape out. Then hopefully this series can take you from that position to a final taper. That's what I want to do with this whole series. So to get started, you should know what a PDK is, and that's what it is. It's just a bunch of files basically which show you, which describe the different models involved and things like that. So if you look at the components, so you have the design rules. So you have several, design rules that you need to follow so that a device can be, or a given circuit can be fabricated successfully. Technology files, for different layers, materials that are used, very complicated process with many metal layers, several dielectric layers, things like that. And then of course the mathematical models of all the devices, which the foundry provides, standard cell libraries. So things like logic gates, flip-flops, standard cells and parametric cells, P cells and standard cells, all of this will be provided in the PDK. And then the DRC, or the design rule check, to make sure you're meeting all the design rules that are set out by the foundry. For different processes, they're different. And then the layout was a schematic, something very important. So essentially you've done a schematic. So you have different components connected together in the schematic. And then you've also done a layout. And to make sure that they both match, you'll do like an LVS. We'll go through all of this obviously as we go through the series, but that's these files will be provided in the PDK. Parametric files and different kinds of documentation is also included. So essentially, this is what a PDK is. Different foundries will provide different PDKs. So for example, TSMC, which is a big foundry, has a 65 nanometer PDK, which is very famous, which is what I've worked with in the past as well. But there are other foundries as well, global foundries, STMicroelectronics, Intel, and so on and so forth. So they all have PDKs. They're highly confidential. So of course you have to sign an NDA in many cases to get access to a PDK. So you should, if you want to get started, you should contact these companies through your university or your company and then acquire PDK, which can be quite expensive, and then sign an NDA and go in that direction, basically, if you want to do that. But in our case, since I'm making these videos public, I'm not going to use any official PDKs from any company. Cadence itself provides a generic PDK called a GPDK, which is what we'll be using. It's exactly like a regular PDK, but it doesn't actually go into any fabrication. It's just a fake PDK in that sense. Okay. So the main purpose is design validation. Make sure that, what you've designed can actually be made. And then to be able to simulate the circuits that you've laid out, things like that. And of course, optimizing your design. So essentially, they are meant to bridge the gap between the design team, which is us, circuit designers, and the manufacturing process, which is the foundry, making sure that this bridge is made between these two people, right? Groups of people. So that's what a PDK is. So enough about that. So let's assume, you get access to a PDK. How do you get started, right? Okay. So to get started, what I will do is I'm going to close this and open Linux. So typically I think Cadence is only available in Linux. So you need a Linux machine for this. So here I have a server from my research group. And what I've done is I have downloaded and extracted this PDK. It comes with Cadence itself. So you can either download it. There are other versions as well, like North Carolina State University, I believe, has like a free PDK that you can use. And then the Skywater 130, which is an open source PDK, which you can actually fabricate with. So these are all different options. So we'll just use the GPDK for now. Okay, so I've downloaded this and extracted this into a folder, which is the PDK folder. So you go into this and then you have all of these things, right? So to understand what all of these things are, let me go back to the slides again. Okay, so we have an IC design environment, right? So, I mean, this is basically the IC design environment. There are three major players in this space. There's Cadence, Synopsys, and Mentor Graphics, which is now acquired by Siemens. So it's called Siemens EDA now. And there are different things to consider, I guess, from these three companies, right? So the first thing to consider is the platform that you use to make your designs. So to do your schematics, layouts, simulations, and verifications. Cadence offers a platform called Virtuoso, and then there are there are other platforms by these companies as well. By these companies as well, but Virtuoso is like the most popular one, right? So that's what we'll be using. And it's very popular because you can use all the tools from other companies as well within Virtuoso. So that's why it's nice, but it's good to know that these exist as well in case you prefer them. Okay. So that's why I have box around it, because that's the most widely used. And then you also have, apart from the platform, you'll have circuit simulators, right? Like SPICE simulators, what they're called as. SPICE was the original one, and then now there are modifications to SPICE, of course. So Spectre is the one offered by Cadence, then HSpice and PrimeSim is by Synopsys, and Eldo and AFS are by Mentor Graphics. So each of them are used for different use cases. So some of them are faster, some of them are more accurate, some of them are used for digital design or mixed signal design or analog design, RF. There are all kinds of different simulators, right? So here there's no really one player one player to rule them all really. All of them have different applications. So in our case, we'll be using Spectre for the most part. And then there's the physical verification, which is the DRC and LVS, which we talked about, the design rule check and the layout versus schematic. So here, Cadence offers Pegasus, PVS, and Ashura. Ashura is an older version, I believe. Pegasus is the latest one. And then Synopsys also has ICV and Hercules. Hercules, I believe, is older. ICV is the newer version. But by far the most widely used tool for physical layer verification is Calibre, which is offered by Mentor Graphics, right? Calibre can be incorporated into Calibre can be incorporated into Virtuoso using some kind of script that they provide. So you can also do that. So that's why it's nice to use Virtuoso, because you can use Calibre with it. And finally, you have parasitic extraction. So this is after you do the layout to extract all the parasitics, which are not included in the original circuit. Different companies offer different parasitic extraction softwares. Quantus QRC, Ashura, and PVS extraction are part of Cadence. Star RC, Primetime SI are from Synopsys, and Calibre again has its own extraction tool. Again, Calibre is, I think, the most widely used. But in our case today, since we're using, in this series, we're going to use the GPDK from Cadence itself, we will stick to this vertical. So we'll use Virtuoso, Spectre, I think PVS or Pegasus, I'll have to decide later, or Ashura, and QRC, Quantus QRC for the extraction. So this is a general sort of overview of the IC design environment. And once you get sort of an idea of this, we'll see these popping up again and again, these names. So it's good to keep this in the back of your head. Okay, so going back to where we were. So once you open the PDK, you see all of these folders. So Ashura is one of the physical layer verification tools that we talked about. Diva was the one before that, so that's an older version. You have some documents. Here you have the PDK with different model files. Another set of models, Spectre models, which is again the circuit simulator. And then PVS was the physical layer verification tool, the newer version of it. That's newer than Ashura and Diva. And then QRC, which is the parasitic extraction tool. I'm actually not sure what this is. Anyways, probably won't be using it. So what's most important here is you go into documentation and you'll see several documents here. These three documents are very important. So in an actual PDK, you should never ever share these or remove them from your server or wherever you're hosting these documents. But in this case, it's a generic PDK, so I can just open it up. Okay, so contemporary report. I want to open the reference manual. Yeah. Okay, so this basically goes through all of the different, data sheets, things like that of all your models and how to set up the PDK itself. So for example, if you go to installation, it'll tell you how to install this. You download the zip file and then you extract it. And then it tells you what all the different directories included and their explanation, I guess. So let's go here. So this is where we want to get started. So this is how to actually set up Cadence so that it can recognize this PDK, right? So you can read these instructions on your own, but I'll do it separate. I'll anyway do this myself. So let's go ahead and get started on that. But anyway, I just want to mention that you can also go through these documents. They have a lot of information. It's very important to actually read the entire PDK from start to end, in case you miss something. So for example, some processes, they have like a 90% shrinkage in the sizing, and you need to account for that when you design passives and things like that, right? And for example, in this PDK, it gives you all the metal layers and all this information that we will be using in the future. So let me see if I can find the stack up for all the dielectric layers. Yeah, here. Okay, this is exactly what we'll be using in the future. So the different metals and their sheet resistance, we'll use this to calculate the conductivities of all the metal layers, and all the dielectric layers, their thicknesses and the dielectric constants, right? These are very important. And you can also see sort of a stack up here. We'll do this stack up in a future video. Okay, so I just want to show you that. So read through this documentation very carefully. Okay, so enough about the PDK, we can get started. So I'll create a new folder called Cadence. Go in there. And now I need to copy the cds.lib. So I'll copy it and then I'll replace it with this line. And then we need to change this directory here, right? So I need to find out what is the directory in which the PDK was installed. So this directory, pwd, that's this one. Copy that. And then put that in here. Save. Okay. That's it. Then there is actually one more file that I need, which tells all the modules that need to be loaded. So I'm actually just going to copy it from one of the previous copies that I made of this. But you don't have to do that. Okay, so I'm going to copy paste it here. So you can make this yourself, CSHRC. You can name it whatever you like, really. So here I'm loading all the modules. So I'm loading Cadence, the Virtuoso environment, Spectre circuit simulator. This is the layout physical verification tool. This is the X tool, the parasitic extraction tool. EMX is for passives like inductors and so on. And I think even Helix is for passives. Probably we won't be using Helix, but we might use EMX. So that's why I'm loading all these modules and I'm telling it, okay, where is the location of my PDK? And that's the environment. So we'll save this. And basically, once you have these two files, for different PDKs, this might be different. So you'll have to check with, like, say, the IT department uh, of your school or your department to see what all modules are loaded. So you need to make sure that these modules are loaded. So I'll say module avail Cadence. That should give me all the Cadence modules that are available. I can use one of them. So I'm using an older version so that I can use an environment that's not really available in the newer version. We'll go through it as we go through it. You'll see why I'm doing that. You can say, for example, module avail PVS. So all of these modules need to be installed by the IT folks of your department, I guess, or if you know how to do it, you can do it. But these were already pre-installed for me, so it was easier for me to get started. Anyways, so once you have this file ready, all you have to do is open terminal, CSH, source, CSH, RC, the file that we just made, and then Virtuoso. You put an and there if you like. Okay, so that should start Cadence for me. Okay, so once that's started up, then you can click on Tools, Library Manager, and you should see the GPDK open up here. Right? If you haven't done it correctly, then your PDK will not show up here. If you did it correctly, then all the models of all your files should show up here. You can say Show Categories, and then let's say we look at the transistors, right? So you have the Spectre model, symbol, layout, everything is included, right? So for example, I can click on the layout. That should open the layout of my transistor. We'll get to the layouts later. For now, this is good. Okay. And you can look at other devices and you can read about the devices here, what the names mean, right? So in the PDK itself, you see NMOS 1V is 1.1 volt, nominal V threshold, NMOS transistor. And then, for example, the others are like different types. So you can read about them, you can Google them and see what these words mean and so on. So now that we have that going, now what I can do is maybe do a very simple simulation of the fmax of this process, right? That's the first thing you should simulate when you start a new process, especially when you're doing millimeter wave kind of circuits. So what we'll do is we'll create a new library. And then I'll call this fmax test. I usually like to label them such that they are in ascending order. And then hit OK. And then say attach to an existing technology library and click on the GPDK. So your PDK of choice. Okay. So that library is created. And then we'll create a new cell view. And then I'll just call this, say, fmax test 1. A0 and fmax test 1. Create the schematic view for it. And then hit OK. So then the schematic should open up. And there are many Cadence hotkeys to do different things. You have to learn them, especially when you're doing layouts. I'll put a file in the description for all the hotkeys that are generally used in Cadence. So it'll help you with getting familiar. But essentially, you can start by hitting I. If you click I, it will place a component. So I can go to GPDK. And then let's say I want to do the 1 volt transistor. Let the length be 45 nanometers. That's the minimum length. I can change the finger width to, what do I change it to? Let's say the channel width, right? Place it. Then I can select it and hit Q, and that'll change the parameters. So I can say number of fingers is anything. Fingers. And all these different parameters, you can play with them if you like. So whether you want a gate connection or not, and so on. Okay. So that's the basic transistor, right? Hit F, it zooms in and into the circuit. So that's another hotkey. Okay, so then we'll hit I again, go to analog library, and then say I want DC supply. Put one there, one there. And then I want, let's say, an inductor. So one inductor here, one inductor here. And then I want a ground. One there, one there, there, there. And then I want ports. We need 2 ports. And I also want some caps. So if I click the center mouse button, it rotates it. Just place one here and one here. Okay. So I hit C, and then I click and drop here. So C just copies an element. It's very different from general Windows, which is kind of something you have to learn, I guess. But W creates a wire. So make these connections. Click there and then click here to make a U-turn. Click this, click this. I'm grounding the body contact. Okay, and then I hit C, click on that, and then click there. And then hit F, and now we have some kind of circuit going, right? It's this connection, this connection, this connection. Okay. So essentially I have RF coupling in from here. So we'll make this very large. I'll make this 1 microfarad. micro. It's also 1 microhenry. So I'm just making it very large. So it's like open. These are like open circuits that are RF, and these are short circuit are RF, right? So that's the basic idea. You shouldn't make them too large. If you make them like 1 farad, for example, it can cause the simulation to have issues, convergence problems. So just make it large enough such that it's like a short. Okay. When I saw I have RF coming in here, it's an open here, so it doesn't go there, it goes in here, and then generates a current in this circuit, and the RF current flows through this because this is short and this is open, right? And then DC path sees an open on this side. DC just goes through this transistor. And the same way here, this DC goes and directly biases this, right? It doesn't see this output. So that's the idea. This is like a bias T. Essentially just 2 bias Ts. Okay, so I also want to change this to, okay, this can be 50 ohms, and this is also 50 ohms. No, I need to change this. So I'll make the DC voltage here, like say 1.2 volts. And this one, I'll call this V8. This should technically be 1.1 volt, but whatever, 1.2 should be okay. Okay, so I think with that we are good. So I'll say launch ADE. That's why I use an older version of Cadence, so I can use this ADE simulation tool. You can change it if you like, but in future videos, maybe we'll look at the more complicated ones like Maestro and ADXL and so on. But for now, we'll just do ADE. You can change this temperature if you like. Typically, these circuits operate at a higher temperature because they heat up. So we can make this, I don't know, 60 or something like that. Then right click and then say copy from cell view. That'll bring in all the different variables that we set. So we'll make this 1 micro. So 1 micron channel width, and let's say 5 fingers. And we'll make this 500 millivolts. Just some numbers to get started, right? Okay, and then we want to add an analysis. So I'll add DC analysis, save the operating point, and then hit OK. And then I also want to add S parameter analysis, SP. So now it's going to tell me to select the ports. So I'll say select this and this. That should give me ports 0 and 1. And then I'll sweep from, let's say, 10 gigahertz to 400 gigahertz. And I'll say, okay, do noise simulation as well. And then the output port should be this one, and input port should be this one. Okay, so those two got selected. And then hit OK. All the other settings you can leave it for now. We'll explore them as time goes on. But for now, that should be good enough. And you can either say check and save and run simulation here, or you can even run simulation here. So we'll wait for the simulation to be done and then continue. Okay, so that's really just took a few seconds. It says 0 errors, 0 warnings, 5 notices. If you run into errors, you should go and take a look at this log and see where the errors were. But for now, we're good. So no errors. So we can start by plotting the results. So results, direct plots, or let's say first annotate DC node voltages. So that shows you all the node voltages, 500 milli, 500 milli. Make sure these are all correct. And then the next thing you want to do is to say maybe results, annotate operating points. So now you see at what points these are operating, right? So you see that the drain current is around 50 microamps. VGS is 500 millivolts. And the GM, small signal transconductance, is around 730. Is that micro? Yeah, micro. So anyways, that's microsiemens, I guess. Okay, so that's the operating point. Whether it's good or bad is a different question. Right now, we're just kind of simulating it to get started, right? Okay, so now what I want to do is I would like to plot the fmax. So I'll say direct plot, main form, y parameters, rectangular plot, real part. I need all 4 real parts. Oh, I forgot to add to outputs. So say add to outputs and then say click on all 4. And then again say add to outputs and click on all 4. So you need the real and imaginary parts of all the y parameters. Okay, then close this, go back to ADE. Since we said add to outputs, now we have all of these outputs, right? So I'll go ahead and rename these G11, G12, G21, 2, B11, B12, B21, B22. Okay. And then I want to create this new function called the U function. And the expression for that is here. We will derive this, or we will look at this in a separate video. But for now, just know that this is the expression, right? Where the star stands for square. Star 2 is squared. Right, so that's the expression for this U function, the Mason's invariant U function, which we'll derive or discuss the theory behind this in a separate video. But that's what is used to define the fmax. So that defines the activity of a transistor, for example. So I'll just say that, and I'll say add. Okay. So then we can actually go ahead and plot this. So I don't want all of these to be plotted. And I hit plot, and that should plot the U function. And I can hit V. That creates a vertical bar. And wherever this hits 1 is the fmax of that process. So in this case, it's around 275 gigahertz, right? So that's what the fmax is for this transistor with this bias condition and this sizing. So that's important as well. It's a function of both sizing of the transistor and biasing. And this is before doing any layouts, before extracting the parasitics of the interconnects, right? So if you want to actually extract this parameter directly, what you can do is you can close this. We'll create a new expression called fmax. And there I put in this unity gain frequency of U, right? So this actually is a function. We'll discuss functions from the calculator later. But essentially, if you do this and I hit OK, then every time you do this, sorry, there was a mistake. Oh, shoot, I deleted the U function. So let me put that back in. So so put it back in, I say U, and then I copy paste that expression again. And I have to say add. Okay, that should work. So now that fmax depends on U, it needs to have U beforehand, right? Okay, so now that we've done that, now you can see fmax, the value is plotted here, right? That's 275.75 gigahertz or so. So that's the maximum frequency at which you can have gain from a given transistor, or activity of transistor acts like an active circuit device or circuit element up to this frequency. That's what the definition of U gives. Okay, so essentially here we've covered what is a PDK, how to set up a PDK. In this case, the generic PDK, but other PDKs can be more complicated. You may need to talk to someone who is sort of an expert in your department, or an IT guy who kind of handles this, IT person who handles this area on setting up PDKs. So once you have it set up, go through all the documentation very carefully, take notes of things like what is the maximum current handling capacity of different metal layers, what is the maximum voltage swing that is allowed between the drain and gate, or the drain and source, or the gate and source. That will stress the transistor, so those things will be mentioned. That's also very important to keep in mind. And then another thing which we will use in a future video is the different dielectric and metal layer thicknesses and conductivities, things like that. And in case there's any shrinkage factor, like a 90% shrinkage factor in different processes, that needs to be kept in mind. And you can also look at the different performance metrics and things like that. So go through all the documentation, and then as a first step, you can just pick a transistor of your choice, try different transistors and simulate the fmax for different bias conditions, different gate bias, different drain volt, like the VDDs, and for different sizings, different finger sizes and number of fingers, things like that. So you can play around with that and see. So in the future video, we'll do that. We'll see how to select, for different designs, how to select the right transistor sizing and bias conditions, things like that. So hopefully that was helpful to get started on chip design. So this is the first video. I've been trying to make this video for a long time. Hopefully I got to it at the end. I'm glad that I got to it at this point. So we have a lot to discuss. We're going to do hopefully an entire system design from start to end. That's my goal with this series. So hopefully you're excited. Good luck. Thank you. See you in the next one.